In October 2017, astronomers at the Pan-STARRS telescope in Hawaii detected something that shouldn't exist. An object moving through our solar system at over 196,000 miles per hour, tumbling end over end like a cosmic cigar. This was Oumuamua, the first confirmed interstellar visitor we've ever detected, and it violated every assumption we had about how objects should behave in space. Its acceleration pattern, its shape, its trajectory, all impossible according to our models. But Oumuamua was just the beginning. Since then, we've discovered objects that don't just challenge our understanding of physics, they shatter it completely. Objects moving in ways that defy gravity. Galaxies that existed before they had time to form. Phenomena that suggest our most fundamental laws of nature might be wrong. These aren't theories. These are confirmed observations that have left scientists scrambling to rewrite textbooks. This is Cosmic Outliers, where we investigate the universe's most confounding mysteries. Let's examine 10 interstellar objects that broke our understanding of physics. Oumuamua entered our solar system from the direction of the constellation Lyra in September 2017, traveling at a speed that immediately told astronomers this object didn't originate here. Its velocity was too high, its trajectory too steep. This was humanity's first confirmed detection of an interstellar visitor, an object that formed around another star, was ejected from that system, and wandered through the galaxy for millions of years before passing through our cosmic neighborhood. What made Oumuamua truly baffling wasn't just its origin, it was its behavior. As astronomers tracked the object, they noticed it was accelerating away from the sun in a way that couldn't be explained by gravity alone. When comets accelerate like this, we see outgassing, jets of vapor from ice turning to gas. But Oumuamua showed no signs of a coma, no tail, nothing that would indicate it was releasing gas. Harvard astronomer Avi Loeb suggested that the acceleration could be explained if Oumuamua was extremely thin and flat, like a solar sail pushed by sunlight. The problem? Natural processes don't create kilometer-long objects that are 10 times longer than they are wide and only a few hundred meters thick. The shape itself violates what we know about how celestial bodies form through accretion and gravitational collapse. Some scientists proposed it might be a hydrogen iceberg, which would outgas invisibly. Others suggested it was a fragment of a disrupted planet. But every explanation required inventing new types of objects we've never observed before. Oumuamua forced us to confront an uncomfortable truth. Either our laws of physics have exceptions we don't understand, or we witnessed something artificial passing through our solar system. Neither option is comfortable. 2 years after Oumuamua, amateur astronomer Gennady Borisov detected another interstellar visitor using a telescope he built himself. This object, designated 2I Borisov, was clearly a comet. It had the tail, the outgassing, everything we expected. Finally, scientists thought, a normal interstellar object we can understand. Except Borisov wasn't normal at all. Spectroscopic analysis revealed that Borisov contained carbon monoxide concentrations higher than any comet we'd ever studied from our solar system. Not just slightly higher, dramatically higher. This suggested it formed in an extremely cold environment, colder than the outer reaches of our own solar system. But here's where it gets strange. The chemical composition of Borisov implied it came from a solar system very different from ours, one where the protoplanetary disk had different chemical ratios. That's fine in theory, but the problem is scale. For us to detect 2 interstellar objects within 2 years suggests these visitors are far more common than our models predicted. If interstellar objects pass through the inner solar system this frequently, there should be thousands of them in our cosmic vicinity at any given time. Yet until 2017, we'd never confirmed a single one. Either our detection methods were catastrophically inadequate for centuries, or something changed recently that's causing more interstellar objects to pass through our region of space. Some astronomers have suggested we might be entering a denser region of the galaxy, an area with more debris from stellar disruptions. Others propose that a recent nearby supernova or stellar collision ejected a massive amount of material that's now reaching our solar system. But we have no evidence for such an event. Borisov didn't just challenge our understanding of cometary chemistry. It challenged our assumptions about the density and distribution of matter in interstellar space. In 2014, 3 years before Oumuamua, a meteor exploded over the Pacific Ocean near Papua New Guinea. At the time, nobody paid much attention. Meteors hit Earth constantly. But years later, Harvard physicist Avi Loeb and his student Amir Siraj analyzed the object's velocity from government sensor data and discovered something remarkable. This meteor, designated CNEOS 2014-0108, was traveling at over 130,000 miles per hour relative to the Sun when it hit Earth's atmosphere. That velocity is too high. It exceeds the escape velocity of our solar system, which means this object came from interstellar space. Unlike Oumuamua or Borisov, which we detected in the void between planets, this object slammed directly into our atmosphere. And here's what broke physics: the material composition. For an object to survive the incredible forces of interstellar travel at those speeds, it would need to be made of something extraordinarily strong. Loeb calculated that the meteor's material strength exceeded that of iron, suggesting it was composed of some kind of alloy or material tougher than anything typically found in natural meteors. The object disintegrated about 12 miles above the Pacific, and fragments should have fallen into the ocean. Loeb organized an expedition to dredge the ocean floor and recovered spherules, tiny molten droplets, from the impact site. Analysis of these spherules revealed an unusual composition with elements in ratios not typically found in solar system materials. The implications are staggering. If this object was indeed interstellar and composed of materials stronger than iron meteorites, it suggests one of two possibilities. Either interstellar space contains formation processes that create materials we don't understand, or this object wasn't entirely natural. Loeb has suggested the latter, but even the former would require us to completely revise our models of how materials form in protoplanetary disks. In March 2023, astronomers detected something unprecedented, an object designated 3I Atlas that appeared to be an interstellar visitor. But unlike Oumuamua or Borisov, this one seemed to be moving impossibly fast. Initial calculations suggested it was traveling at speeds that couldn't be explained by any known ejection mechanism from another star system. For an object to reach such velocities naturally, it would need to have been accelerated by something catastrophic, a supernova, a black hole encounter, or a stellar collision. But the trajectory didn't match any of these scenarios. The object's path didn't trace back to any known stellar remnant or high-energy region. It came from empty space. As astronomers continued tracking the object, something even stranger emerged. Its velocity appeared to be changing in ways inconsistent with gravitational influences from the Sun or planets. The acceleration wasn't constant like Oumuamua's. It was erratic, almost like course corrections. This kind of behavior has never been observed in any natural celestial object. Some scientists propose that 3I Atlas might be fragmenting, with pieces breaking off and changing its momentum through a rocket-like effect. But no fragmentation was observed, no debris trail, no change in brightness that would indicate the object was breaking apart. It just kept accelerating and decelerating in patterns that defied explanation. The most unsettling aspect is what this implies about our detection capabilities. If objects can move through our solar system with velocities and trajectories this anomalous, how many have we missed? How many pass through the space between Earth and Mars without ever being detected because they're moving too fast or in directions we're not monitoring? In early 2024, the James Webb Space Telescope captured images of a galaxy designated JWST 14-0 that existed just 290 million years after the Big Bang. This might sound like an interesting cosmological footnote, but it's actually a complete violation of our understanding of how galaxies form. According to our models, galaxies this large and this bright shouldn't exist so early in the universe's history. The Big Bang occurred 13.8 billion years ago. In the first few 100 million years, the universe was filled with hydrogen and helium gas, but no stars had formed yet. This period is called the Cosmic Dark Ages. Stars began forming around 200 to 400 million years after the Big Bang, and those stars then began clustering into the first proto-galaxies. But this process takes time. For a galaxy to reach the size and luminosity of JWST 14-0, it would need hundreds of millions of years of star formation, matter accretion, and gravitational assembly. Except it didn't have that time. It existed when the universe was barely 2% of its current age. The galaxy is far too massive, too bright, too structured. It contains billions of stars when our models say it should contain millions at most. Several astronomers have proposed exotic solutions. Maybe the first stars were far more massive than we thought, burning brighter and faster, seeding galaxies more quickly. Maybe dark matter clumps in the early universe were denser than our simulations predict, allowing matter to collapse into galaxies faster. Maybe the laws of gravity operated slightly differently in the extreme conditions of the early universe. But every solution requires abandoning assumptions we've held for decades. The existence of this galaxy suggests our entire timeline of cosmic evolution is wrong, and it's not alone. JWST has found multiple galaxies from this era that are far too developed. We're not talking about one anomaly. We're seeing a pattern that demands we rewrite the first chapter of cosmic history. In the constellation Ophiuchus, astronomers discovered a supermassive black hole that appears to be moving through space at over 3 million miles per hour, leaving a trail of disrupted stars in its wake. This object violates conservation of momentum in ways we can't explain. When black holes form from stellar collapse or merge with other black holes, they can receive a gravitational kick from asymmetric mass ejection. These kicks can propel black holes at high speeds, but the velocities we observe should max out around 600,000 miles per hour based on our models of supernova mechanics and black hole mergers. This object is moving 5 times faster than that maximum. To achieve such velocity, the black hole would have needed to be involved in an incredibly asymmetric merger, one where the two black holes had vastly different masses and spin orientations, and where the gravitational wave emission was concentrated in one direction with unprecedented efficiency. The problem is, we've never observed such a merger. We've detected dozens of black hole mergers through gravitational waves, and none have produced kicks anywhere near this magnitude. Some physicists have suggested the black hole might have encountered a third massive object in a gravitational slingshot scenario, using the gravity of another black hole or dense stellar cluster to accelerate to these speeds. But the trajectory doesn't support this. The black hole isn't coming from any known dense region that could provide such acceleration. It's moving through relatively empty space, dragging a wake of disrupted stellar material behind it like a cosmic speedboat. What makes this even more confusing is the stability of that wake. At these speeds, the turbulence and gravitational interactions should shred any trailing material quickly. But the wake persists, maintaining coherence over distances that shouldn't be possible given the velocity and the gravitational environment. This suggests either our fluid dynamics models for interstellar gas are incomplete, or there's some mechanism stabilizing the wake that we don't understand. Magnetars are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. They're already extreme objects. A teaspoon of neutron star material would weigh 1 billion tons on Earth. But in 2020, astronomers detected a magnetar designated SGR 1935+2154 that did something impossible. It emitted a fast radio burst. Fast radio bursts are intense pulses of radio energy that last just milliseconds but release more energy than the sun emits in days. For years, scientists debated what caused these bursts: colliding neutron stars, evaporating black holes, even alien transmissions. But detecting one from a magnetar in our own galaxy changed everything. Except the magnetar's behavior doesn't match what we know about how these objects work. Magnetars emit X-rays and gamma rays when their crusts crack and release magnetic energy. We understand that process. But converting magnetic field energy into coherent radio bursts requires physics we haven't figured out. The energy conversion efficiency would need to be impossibly high, approaching 100%. No known physical process is that efficient. Some astrophysicists propose that the magnetar might be surrounded by an ultra-dense plasma that acts like a cosmic laser, converting magnetic energy into radio waves through some kind of Massar effect. But creating and maintaining such a plasma around a magnetar would require conditions we've never observed. Others suggested quantum effects might play a role, that at the extreme densities and magnetic field strengths near a magnetar's surface, quantum electrodynamics behaves in ways our current theories don't predict. This is plausible, but untestable with current technology. What's most troubling is the implications for our understanding of neutron stars. If magnetars can produce fast radio bursts, and if fast radio bursts are more common than we thought, then our census of neutron stars might be completely wrong. There could be thousands of these objects in our galaxy that we've misidentified or never detected, because we weren't looking for the right signals. In a galaxy cluster designated El Gordo, astronomers observed two massive galaxy clusters colliding at speeds that violate our models of dark matter and gravity. Galaxy clusters are the largest gravitationally bound structures in the universe, containing thousands of galaxies and vast amounts of dark matter. When two clusters collide, we can observe how the ordinary matter, dark matter, and hot gas interact. In most collisions, the dark matter passes through relatively unaffected because it doesn't interact electromagnetically. It only responds to gravity. The ordinary matter, especially hot gas, slows down due to collisions and friction. We can map this by observing the X-ray emission from hot gas and using gravitational lensing to track where the dark matter is concentrated. In El Gordo, the collision is happening at over 4 million miles per hour, far faster than our simulations predict is possible. For clusters this massive to be moving this fast relative to each other, they would have needed an enormous amount of kinetic energy at the moment they began falling toward each other. That energy has to come from somewhere. In our standard cosmological model, that energy comes from the expansion of space and the gravitational attraction between the clusters over billions of years. But the numbers don't add up. To reach the observed collision speed, the clusters would have needed to start from a much greater distance than cosmological models allow, or they would have needed some additional source of acceleration. Some cosmologists have suggested this might be evidence that dark energy, the mysterious force causing the universe's expansion to accelerate, behaves differently on cluster scales than we thought. Maybe dark energy isn't uniformly distributed, but has fluctuations that could accelerate massive structures in unexpected ways. Others propose that our understanding of gravity on these enormous scales is incomplete, and that Einstein's general relativity needs modification when dealing with structures containing quadrillions of solar masses. But modifying general relativity is extraordinarily difficult. The theory has passed every test we've thrown at it for over a century. Changing it to explain El Gordo risks breaking its predictions for everything else. Yet the collision speed remains unexplained by conventional physics. The Bode's void is a region of space nearly 330 million light-years in diameter that contains almost no galaxies. Most of the universe is arranged in a cosmic web, filaments of galaxies separated by voids. But voids usually contain some galaxies, just fewer than average. The Bode's void contains only about 60 galaxies in a space where we'd expect to find 2,000. This emptiness violates our models of structure formation. After the Big Bang, matter was distributed almost uniformly with tiny density fluctuations. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter and became galaxy clusters and filaments. Less dense regions became voids. But this process is gradual and continuous. You shouldn't get regions this empty because even low-density areas should have some matter that eventually collapses into galaxies. For the Bode's void to be this empty, something would have had to remove galaxies after they formed, or prevent them from forming in the first place. Several explanations have been proposed. Maybe the void was once normal, but then a massive structure collapsed into a supervoid, pulling galaxies out of the region toward the edges. But we don't see evidence of unusually dense structures surrounding the void that would account for all that missing mass. Another idea is that the void represents a region where dark energy is slightly stronger than average, causing space to expand faster and preventing matter from collapsing into galaxies. This would require dark energy to vary spatially, which contradicts our assumption that it's a cosmological constant, the same everywhere. Some physicists have even suggested the void might be a remnant of bubble nucleation from the early universe, a region where the quantum fields that drive inflation settled into a different energy state. But this is purely speculative and nearly impossible to test. What makes the Bode's void particularly unsettling is the question it raises about other voids. If one void can be this anomalously empty, how many others are out there that we haven't fully mapped? And if voids this extreme can exist, what does that say about the uniformity of physical laws across cosmic distances? In 2019, astronomers detected gravitational waves from a collision between two black holes, designated GW11900521, that shouldn't have been able to form through stellar evolution. One of the black holes had a mass of about 85 times the Sun. The other was around 66 solar masses. When they merged, they created a black hole of roughly 142 solar masses. That final mass puts it squarely in a range we call the intermediate mass black hole gap, a mass range where black holes theoretically shouldn't exist. Here's why. When massive stars die, they can collapse into black holes. But there's a mass range between about 65 and 120 solar masses where something different happens. Stars in this range undergo pair instability supernova, explosions so violent that they completely destroy the star, leaving no remnant behind. No neutron star, no black hole, nothing. Above 120 solar masses, stars can collapse directly into black holes again. Below 65 solar masses, normal supernovae can leave black hole remnants. But in that gap, the physics of stellar death should prevent black hole formation entirely. Yet, GW190521 involved black holes with masses right in that forbidden zone. The 85 solar mass black hole especially shouldn't exist. To explain this, astrophysicists have proposed that these black holes didn't form from single stars, but from previous black hole mergers. Smaller black holes that collided and merged, building up mass in stages. But this creates its own problems. For black holes to merge multiple times and build up to these masses, they'd need to be in an extremely dense environment where encounters are common, like the center of a globular cluster or a galactic nucleus. And even then, the timescales are problematic. Each merger takes time, and the merged black hole needs to lose enough energy through gravitational wave emission to stay bound in the cluster and encounter another black hole. Some physicists have suggested these might be primordial black holes that formed in the first moments after the Big Bang from density fluctuations, not from stellar collapse. Primordial black holes wouldn't be constrained by the physics of stellar evolution and could have any mass. But we have no direct evidence primordial black holes exist. They remain purely theoretical. GW190521 is now one of dozens of gravitational wave detections that challenge our models. The more black hole mergers we observe, the more we find masses, spins, and configurations that don't match what stellar evolution predicts. Either our understanding of how massive stars die is fundamentally incomplete, or we're detecting a population of black holes that formed through processes we haven't discovered yet. These 10 objects represent more than anomalies or outliers. They represent cracks in the foundation of physics. Oumuamua accelerated without outgassing. Borisov contained chemistry from an alien star system and appeared more frequently than probability allows. The 2014 Interstellar Meteor was made of materials tougher than iron. 3I Atlas moved with velocities and trajectory changes that defied gravitational explanation. JWST Z140 existed before it had time to form. The runaway black hole in Ophiuchus moved 5 times faster than any ejection mechanism should allow. The magnetar SGR 1935+2154 emitted energy in ways that require impossible efficiency. El Gordo's collision happened at speeds our cosmology can't explain. The Bootes void is emptier than structure formation allows. And GW190521 involved black holes from a mass range where black holes shouldn't exist. Every single one of these observations has been confirmed by multiple independent teams using different instruments and methods. These aren't errors or misidentifications. They're real phenomena that demand explanation. And here's what keeps scientists awake at night. We only detect a tiny fraction of what's out there. For every Oumuamua we spot, thousands pass unnoticed. For every impossible galaxy JWST photographs, hundreds remain beyond our detection threshold. For every gravitational wave we capture, countless mergers happen too far away or too faintly for our instruments to register. We're seeing the tip of an iceberg, and the parts we can see don't make sense, which means the parts we can't see might be even stranger. Physics is built on the assumption that the laws of nature are universal, that gravity works the same everywhere, that thermodynamics applies equally in all regions of space, that the fundamental constants remain constant. But these objects suggest that assumption might be wrong. Maybe the laws of physics have exceptions we haven't discovered. Maybe they evolve over cosmic time. Maybe they vary across space in ways too subtle for us to have noticed until now. Or maybe, and this is the possibility that both excites and terrifies physicists, maybe we're on the verge of a paradigm shift, like the one that happened when quantum mechanics overturned classical physics in the early 20th century. Maybe we're about to discover that our entire framework for understanding the universe is just an approximation, a useful model that works in most cases, but breaks down under extreme conditions we're only now beginning to observe. If you want to follow these cosmic mysteries as they unfold, hit that subscribe button because new discoveries are being made every week that challenge what we thought we knew. Drop a comment and let me know which of these objects disturbed you the most, or if you think there's a conventional explanation we're missing. This is Cosmic Outliers, where we investigate the universe's most confounding mysteries, one anomaly at a time.